when you first started trying to find derivatives, we pretty much had one tool for finding a derivative of a function, and that was the limit definition. And, it worked, but for some kinds of functions, it was a little bit cumbersome, and for some kinds of functions, we had to do some pretty funky algebra tricks to end up with a derivative. And so what we did was make some observations and develop some general rules for how we take derivatives of certain kinds of functions so that we could get away from having to use just that limit definition every single time. Right now, pretty much the tool we have for finding antiderivatives is what function is this the derivative of, which is fine if it's one that we can recognize easily, like this. Whose derivative is 2x? Well, x squared plus any constant. And I know that because the derivative of a function that looks like that is 2x, my integrand. What I'd like to do is the same thing we did for derivatives, to come up with some general rules for certain types of functions so that we can kind of expand our vocabulary of functions whose antiderivatives we can find easily. For example, what if instead of 2x I just have x? Well, the antiderivative for x has to be something to do with x squared, because when I take a derivative of x squared, I get x to the first power. But the constant isn't going to work. If I try to take the derivative of x squared plus a constant, I'm going to get 2x. I don't want to get 2x. I want to get x. But we can fix constants using multiplication and derivative. Multiplication and division. If I put a 1/2 out here, so that I have 1/2 of 2x, there's my x. Well, if there's a 1/2 there, then there was a 1/2 here, which means my antiderivative is 1/2 x squared plus a constant. Since when I take a derivative of a function that looks like that, I get 1/2 times 2x, which is x. So we can fix constants. Let's do the same thing with 3x squared. This is one that hopefully you are yelling at your computer screen. The antiderivative is x cubed plus a constant, because we know that if I take the derivative of that function, I'm going to get 3x squared, which is what I wanted. But then again, what if I leave off the 3? Now it's not quite the same. I know that it has to be some kind of x cubed, the antiderivative. And I know there can be a constant there because the derivative of a constant is 0. But the derivative of x cubed is 3x squared, and I only want 1x squared. Well, we can fix constants. If I want this to be a 1, I can multiply it by 1/3, which means I was multiplying it by 1/3 out here. 1/3 times 3x squared is 1x squared, which is how I needed it to turn out. So my antiderivative here is 1/3 x cubed plus a constant, since when I take a derivative of that, I'm going to get x squared like I wanted. Think about this one in the same vein. What if I'm looking for an antiderivative of -2 over x to the third. Whose derivative is that? Well, that's maybe a little bit less obvious. Maybe it helps if we call that negative 2 times x to the negative 3. And go from there. Well, let's see. If the derivative is x to the negative 3, that means my original function had something to do with x to the negative 2. Oh. X to the negative 2, 1 over x squared, but of course plus a constant. When I take a derivative of that, I get negative 2 times x to 1 lower power, x to the negative 3, which is, in fact, negative 2 over x to the positive 3, which is what I wanted. What if I have just negative 1 over x to the third? Same philosophy as the last couple. It has to be something to do with x to the negative 2 to make the power turn out right when I take a derivative. When I take a derivative of x to the negative 2, I get negative 2 x to the negative 3, but I only want negative 1 x to the negative 3. We can fix constants by multiplying and dividing. If I multiply this by half, there's my negative 1 x to the negative 3, which is what I wanted. So when I multiply that back together, negative 1 over x cubed, which is what I want. What did I have to do? I had to put a half in there to make the constants work out right. These are all power functions, x raised to a power. Let's take a look through here at what's happening and see if we can come up with a nice general power rule for integration. When I integrated x, I got 1/2 x squared. So the power went up by 1. Hopefully that makes sense. Since we're taking antiderivatives, the power goes up by 1. When we took derivatives, it went down by 1. The inverse goes up by 1. And I have this 1/2 out in front, which is 1 over the new power. For x squared, power went up by 1, 1 over the new power. For x to the negative 3, power went up by 1. Negative 3 plus 1 is negative 2. And 1 over the new power. And this is actually that. 1 over negative 2. And the negative sign needed to be in there. So in general, for integrals of power functions of x raised to a power, that's going to go like this. The integral of x raised to a power with respect to x. X is going to go to 1 higher power. And I'm dividing by the new power. Plus our constant of integration. So sometimes you see it written like that. I tend to do it like this. X to the n plus 1 over n plus 1. Whichever way makes more sense to you is fine. They're exactly the same. Let's try it out. The integral of y to the 9th with respect to y. I'm going to raise my exponent by 1. 9 plus 1 is 10. And divide by the new power. Y to the 10th over 10, or 1/10 y to the 10th. plus the constant. Done. So we don't have to wade through that whole thought process anymore. We have a general rule for integrating power functions. 1 over x to the 6th is x to the negative 6. If it's helpful to rewrite it like that, by all means do. When I find an antiderivative, I'm going to have x to the negative 6 plus 1 over negative 6 plus 1. And of course we won't stop there. This is x to the negative 5 over negative 5. And let's not have negative exponents. Negative 1 over 5x to the 5th. Squish my constant in there. It is so important that it is worth squishing it in. Then we have fun things like this next one. Again, rewrite, just like we did with derivatives, really. Rewrite with an exponent. This is t to the root is the denominator. The power is the numerator. So this is t to the 7/4 power. When I find the antiderivative, this is t to the 1 higher power over 1 higher power. We're definitely not going to leave it like that with the complex fraction. 7/4 plus 1. If you can do that in your head, that's great. 7/4 plus 4/4 is 11/4. So I have t to the 11/4. T to the 11/4 over 11/4, which is, we don't want to leave that either. That's a complex fraction. We don't want those. Dividing fractions, multiply by the reciprocal. Oh, I left out my plus c everywhere. Shame on me. Let's put that in. So this is 4/11, t to the 11/4 plus c, and that power rule for integrals will work for any power function.